The first images hit like an alarm, a dark plume, and a sudden alert in mission logs. Within hours, NASA moved from routine watch to elevated monitoring. The mood shifted from curiosity to urgent focus. Control rooms filled with diagnostics and rapid-fire messages. For weeks, teams had tracked 3I Atlas as it moved inward, predictable and quiet. Then, ultraviolet spectrographs registered a sharp spike in hydroxyl emissions, the spectral fingerprint of water being broken apart by sunlight. Initially, engineers suspected a calibration glitch. Instruments fail. Data misreads happen. Calibration checks ran through the night and were soon ruled out. The spike persisted. It rose, wave after wave. Independent observatories around the world confirmed the same pattern: violent, sustained outflow where none should exist. A metaphor spread through scientific channels: a broken engine, a fire hydrant in space, because the visuals demanded something blunt and physical: a sudden, high-pressure venting at 3 astronomical units. NASA framed it clinically. A rapid increase in water loss implies a structural change. There was no slow ramp-up, no precursor brightening, no gradual warming. Instead, 3I Atlas appeared to flip states almost instantly, as if a seal had failed and trapped volatiles found an escape route. The numbers made the contradiction unavoidable. At nearly 3 astronomical units, sunlight is weak. Ordinary comets barely release a trace. Yet, hydroxyl measurements imply continuous, large-scale venting mass loss on the order of tens of kilograms per second, confirmed across separate spectral datasets. Thermal models say this should be nearly zero. Reality says otherwise. That gap forced hard questions. What energy source is driving the outflow? Did a deep fracture expose pristine ice? Is trapped pressure forcing vapor through a rupture? Each hypothesis fits part of the picture and fails elsewhere, complicating everything. 3I Atlas is interstellar. Its surface has been reworked for billions of years by cosmic rays, likely producing a hardened shell that should have kept interior ices sealed. For now, one clear fact remained: the signal kept rising, and routine tracking had become emergency monitoring. Telescopes were retasked, observation windows expanded, and teams moved from modeling to contingency planning. The data did not lie. Something fundamental had changed on 3I Atlas, and until the cause is identified, NASA will watch closely. Hydroxyl OH is the smoking gun. In ultraviolet light, water molecules broken by sunlight leave a clear spectral fingerprint. Teams stopped treating the early spikes as glitches. The signal was real, repeated, measurable. Converting OH intensity to mass loss is a careful chain of inference. Observers turn UV line strength into OH production rates, then back to parent water. Multiple independent groups ran the math and converged on a startling figure: tens of kilograms of water every second, a steady plume, not a brief puff. That rate matters because distance sets expectations. At roughly 3 astronomical units, solar energy is weak. Ordinary comets are essentially dormant, their ices insulated beneath crust. Hydroxyl at this scale implies sustained exposure of interior material or a pressurized release, not simple surface warming. A leading mechanical explanation is sudden crustal failure. Cosmic ray processed shells hardened over eons can trap volatiles beneath. Lab studies show when such a seal cracks, outgassing can leap from near zero to explosive. Sunlight on freshly exposed ice would supercharge the flow, producing a water-dominated jet consistent with the UV chemistry. But fracture doesn't close the case. Large-scale venting should produce measurable thrust. Outgassing is rocket physics. Mass streaming one way pushes the nucleus the other. Models predict a clear acceleration profile for tens of kilograms per second. 3I. Atlas shows some motion but not all. Residuals contain inconsistencies. Simple venting cannot fully explain. Scientists have proposed fixes: a misaligned jet averaged over rotation, multiple fissures emitting in offset directions, or a varying conduit producing fluctuating force. Each tweak helps, but no model yet yields a clean match across optical and dynamical datasets. Composition adds complexity. Hydroxyl implies water dominance, yet earlier spectra showed carbon-rich emissions. Different volatiles vaporize at different temperatures. A layered interior might release CO or CO2 earlier, with pristine water revealed deeper down. A deep reservoir exposed suddenly could temporarily overwhelm usual chemistry and dynamics. The contradiction is stark. Repeatable UV evidence for large-scale water loss at a distance where thermal physics predicts near-zero activity, and a motion profile that only partly reflects expected thrust. Hydroxyl tells a story of flow. The trajectory whispers that something else or something more complex is happening inside. That mismatch drove teams to escalate monitoring and contingency planning. 3I Atlas is not a routine comet. It is an interstellar traveler, a body that likely drifted between stars for billions of years, exposed to a steady rain of cosmic rays that slowly rework its chemistry. That ancient weathering matters. It produces a hardened, dark shell, unlike the thin crusts formed by solar heating inside our system. Cosmic rays break bonds, darken ices, and build layers of processed, carbon-rich material. Over eons, those processes can create an armored mantle meters deep. Estimates often cite 15 to 20 meters, a barrier that should keep interior volatiles sealed until the object is much closer to a star. Size compounds the mystery. 3I Atlas is larger and more massive than previous interstellar visitors. Such bodies are rare. Ones that plausibly retain deep, pristine reservoirs after galactic exposure should be rarer still. Yet ultraviolet fingerprints show water streaming outward, as if fresh ice were exposed now. A crust fracture explains the abruptness in one stroke. Armor fails, trapped pressure finds a channel. Lab studies of irradiated ices show how a brittle seal can snap, turning a near-silent body into a violent vent almost instantly. Sunlight on newly exposed interior ice would supercharge vapor release, producing a water-dominated jet consistent with the hydroxyl spike. That pressure valve image fits the chemistry and the sudden switch, and it explains why the flow is water-rich rather than co-dominated. Deep layers untouched since formation could hold abundant water ice, unprocessed by cosmic rays, and blasting them into sunlight would produce the observed UV signature. Yet physics complicates the picture. Massive venting generates thrust. Mass streaming one way should nudge the nucleus the other. With tens of kilograms per second, the acceleration should be clear and predictable. It is not. The trajectory shows anomalies, subtle, irregular deviations that simple outgassing models fail to reproduce cleanly. Researchers have proposed fixes. An angled jet averaged over rotation, multiple fissures emitting in offset directions, a conduit that widens or narrows with temperature. Each tweak improves the fit, but none resolves the mismatch entirely. The longer the plume persists, the harder the numbers become to reconcile. So the contradiction sharpens: an ancient, armored body that should resist water loss, a sudden, massive vent suggesting exposed, pristine ice, and motion that refuses to obey the straightforward physics of thrust. Those three facts now collide at the heart of the mystery, and time is not on our side. The geometry of the moment turned the mystery into a blind test. As 3I Atlas crossed the line of sight, it slid behind the sun, and the instruments that had been watching the eruption fell silent. No optical imaging, no ultraviolet spectroscopy. The object's most violent hours, the interval when a freshly opened conduit would either starve or widen, happened in darkness. That blackout is decisive. We lose time-resolved chemistry, the immediate color shifts, the early dust signatures, the fingerprints that differentiate a single burst from a sustained vent. Ground observatories can only wait. Orbiting ultraviolet spectrographs are blinded by solar glare. For days, the event will be inferred, not observed. Teams reran models and drafted coordinated campaigns. Radio arrays poised for non-optical emissions, infrared instruments ready for thermal anomalies, wide-field imagers on standby to catch the first coma brightening. Every instrument had a prioritized sequence. What will scientists check when 3I Atlas returns? The coma. If the fracture was temporary, hydroxyl strength should fall, the OH spike will weaken, dust production slow, and brightness curve stabilize. Grain sizes would shift toward heavier, fallback particles. If the fissure is a stable conduit, the coma could expand. Hydroxyl signatures would stay high or climb. Fine ice crystals could scatter blue light and shift the color. Thermal detectors might record cooling in the vent while adjacent areas warm. Those markers would point to a deep reservoir newly exposed. Trajectory is equally telling. Outgassing is thrust. Tens of kilograms per second should nudge the nucleus. If post-conjunction astrometry follows thrust-driven models, venting explains the anomaly. If residuals persist, oscillating accelerations or unexplained deviations, rotational smearing, multiple jets, or internal mass changes might be required. Composition will be watched closely. Early spectra suggested carbon-rich emissions earlier, then an abrupt water rise. Post-conjunction chemistry will reveal whether water dominates or the object continues to flip between volatile regimes. Timing will decide data quality. The first hours after reappearance are precious. Telescope schedules, weather, and residual sunlight limit what can be captured. Teams have preloaded sequences to maximize those minutes. Observers worldwide hold their breath as instruments come online in synchronized sequence. The result will be one of two clear outcomes: a transient valve that closes and leaves a comprehensible object, or a persistent conduit that opens a long window into a primordial interior. Both force us to rethink interstellar bodies, cosmic ray processing, and volatile preservation. For now, scientists wait through the dark. When 3I Atlas reemerges, the observations will point toward a natural explanation or toward something far less ordinary. What follows will change how we model small bodies, or at least force careful revision. The immediate checklist is compact and urgent. First, confirmation. If hydroxyl and dust drop after conjunction, the event will read as a transient fracture. Scientists will update crust failure models, adjust thermal timelines, and note that even dramatic vents can be brief. Second, persistence. If water plumes remain strong, the implication is deeper, a sizable, unprocessed reservoir exposed after billions of years. That would upend expectations about cosmic ray depletion and mark 3I Atlas as an unprecedented window into primordial ice. Third, dynamics. If trajectory residuals keep diverging from thrust models, we confront internal asymmetries, rotating jets, or mass redistribution. Navigation and modeling tools would need revision. Mission planners would take note. Programmatically, the event could shift priorities. Observatories will refine rapid response cadences. Agencies may value nimble, taskable platforms for future interstellar visitors. The case argues for moving from passive watching to proactive interception strategies. Philosophically, a preserved interior is a time capsule chemistry older than the sun, isotopic clues about planet formation, a record of pre-solar processes. That isn't just technical, it touches the origin story of our system. Caution is vital. Scientists avoid sensational leaps. The process is hypothesis, test, revise. Yet uncertainty is productive here. It forces new observations and sharper models. Practically, the first hours after reappearance will be decisive. Teams have preloaded observation sequences. Weather and scheduling will determine how much we capture. Color, coma, expansion, dust-to-gas ratios, and precise astrometry will be parsed immediately. In the medium term, research teams worldwide will publish rapid notes, simulation groups will run new scenarios, and mission concept studios will reevaluate small, fast missions. Funding agencies will watch. A clear, reproducible anomaly could spur targeted calls for proposals. Science proceeds through such pivots. Remote possibilities remain: unexpected organics, layered chemical records, or unusual isotopic signatures. Those outcomes are low probability but high impact, worth watching for, but not assuming. When 3I Atlas returns, the data will compel us to edit textbooks or refine parameters. Either way, the event already matters. It shifted observing priorities, exposed gaps in our models, and reminded us that interstellar visitors can surprise. For now, the world waits. Telescopes are poised, teams are ready. When the first signals pierce the glare, we will know whether this was an extraordinary, contained event or the opening chapter of something far stranger.